So in the first lecture we introduced basic notions of large deviation theory, applying it to a simple example first of a coin tossing and then of frequencies of symbols in an alphabet. Today we look at one fundamental principle of large deviations, which is the contraction principle, which regulates what the rate function of a variable, which is a function of another random variable for which we know the rate function can be derived. And then we move on to Markov processes. So, contraction principle. As usual, I will give you the theory by examples and then tell you just how to generalize. So the example is we take an alphabet of 3 letters, A, B, and C, and we assume that we can sample letters, the symbols independently one of the other, with probability row A equal to row B equal to row C equal 1/3. Okay, and now let's extract this letter n times, and we look at the empirical frequency XA, XB, and XC of finding letter A, B, and C, such that, of course, XA plus XB plus XC is equal to 1. So we have derived before the rate function for this process. It was given by this relative entropy. So f x, now x is A, B, C in general altogether, is XA log XA plus XB log XB plus XC log XC plus 3 log 3. Okay? Simple as that. And now the point is to what we want to do is we want to consider now a new aggregate variable, which is xval, let's say, which is the frequency of vowels, and then we consider xcon, which is the frequency of consonants. Okay, so xb plus xc. Okay, so now this is a function of the original empirical frequencies, which goes from 3 variables to 2. We want to know the rate function f of these new joint variables. So let's call it f x vowel, x consonant. Okay. The question is, well, we can derive it directly from the formula that we already have of the relative entropy, of course. We know that this is going to be x vowel log x vowel 1/3, and then over 2/3. This is just applying our usual formula, again on the constraint that x vowel plus x consonant is equal to 1. But the question is, given that these new variables are functions of the old ABC variables, can we obtain this rate function from this rate function somehow? And the contraction principle says, yes, you can do it, and that you do it by taking the infimum of this function with the constraint that your x vowel, your x consonant take the values that they want to observe. So more precisely in general, suppose you have a collection of random variables x with rate function f(x) of s, and now you have a function y which is some function y of x, okay, new stochastic variable. The question is, how do we obtain f(y) of some values y? Well, the answer is just that contraction principle. Fy of y is just given by the infimum over x, such that y of x is equal to y of f plus x. This is the general formulation. So let's see if the principle works in the case of so we have that our, in this case, y of SA, SB, SC is SA, SB, SC. So the statement is that f x vowel, x consonant is given by the infimum over xa, xb, xc. They have to sum up to unity, and such that xa is x vowel and xb plus xc is s consonant of the f of xa is b. See? Okay, now we can use these constraints, we can just plug them in directly. So in the end we find that this is just the infimum over xc, for example, we can keep xc of f x vowel x consonant minus c s c. So here I have used my constraints, I plug them in directly, so now I don't have constraints anymore, and this minimization I can just do it by taking the derivative with respect to c of the rate function that we know, setting it to 0, finding the solution and plugging the value inside. So we do d over dxc okay. Find the solution, which is log xc. Which gives that xc is half. Okay, so this has an obvious interpretation. The most probable value of the frequency of letter C will be given by the most probable by the value of the consonant halves. Okay, so this by the contraction principle. The contraction principle, what it does, it finds the most probable value of the all variables given the new value of the constraints, which is the number of consonants. So now you plug into the original expression and you will obtain, so you have the original expression was xi log a plus b log xb plus xc log xc plus log 3, something like this. So now you plug in all of your constraints and the solution to this equation, and this will give you precisely s vowel log s vowel third plus s consonant log s consonant 2/3, which is the one solution that we also obtained directly. So this is the contraction principle at the level of the rate function. Again, so we take a function, a new stochastic variable, which is a function of the old stochastic variable. To find its rate function, you have to take the infimum over all possible values of the rate function of the original variable with the constraint that you want to observe the new values of the variable. Okay. Now, again, as usual, we also like to work with the scale cumulant generating function. So the question is contraction principle. How does it work for the scale cumulant generating function? And so let's start from the moment generating function gx of q, which is the usual sum over x probability x e to the q x. And now we have a new, this is the old variable, let's say x. So now we have our new y function y of x, and we want to find gy of a new parameter, let's call it q prime, equal sum over y probability of y e to the q prime y. Okay. We want to see if we can write gy in terms of gx. Okay. For the rate function, it was a minimization problem. Now in this case, how do we do this? Let's first write the probability of y in terms of the probability of x. How does it look? Well, the probability of y is just the sum over x of the probability of x, and then we put a delta, Dirac or Kronecker delta, depending on whether these are continuous or discrete variables, stating that y must be equal y of x. Okay, that's how probabilities work. So let's plug this into this expression here. Is equal sum over y and x, probability of x, delta e to the q prime y. But sum over y, the delta, now this sum over y acts with the delta, so we can discharge the delta and just plug the value of the delta in the expression of y, so we obtain sum over x, probability of x, e to the q prime y of x. Okay? And we want to compare this to gx cube, which is sum over x dx e to the cube x. Well, notice that we don't go much further here unless y is a linear function of x, because if it is a linear function then we have the same structure as here, and so maybe we can do something, but unless if it's not a linear function, then we will not be able to go much further. So let's assume that y of x is a linear function. So we write it as y of x. Now this y is a matrix, okay? And in this case we have that gy q prime is equal to sum over x with x e to the, we can write the transpose acting on q prime, so it's x times y transpose on q prime, okay? And now this acts as our parameter q here, so we see that this is just gx evaluated at y transpose q prime. So this is very nice. When the function is linear, we can formulate a contraction principle at the level of the scale cumulative generating function, and the contraction principle states that so if the function is linear in the sense that it multiplies x, that it evaluates a matrix on x, then the dual variable to x, which is q, will be evaluated on the transpose linear transformation. And that's a very simple way to formulate the contraction principle. So we can go back to our example of the three-letter alphabet. In that case, we had the G of, let's call it ABC, was logarithm e to the q alpha I plus e to the qb plus e to the qc thirds. And now, so the receipt is that you have to just plug in the values of transpose q prime. So what we obtain is that the G vowel consonant is just the logarithm of E of Q vowel plus 2 E to the Q consonant. So you see it's very easy in this case. In this case, just you replace the vowel, the QA of the vowel with Q vowel, and the QB and QC, which are consonants, with Q consonants. We get a 2 here, and that's just how it works. Okay, so now the next topic, we have studied large deviation for independent, identically distributed random variables. Now we look into large deviations for Markov processes. So you may be wondering at this point, where are the spectral methods so far? This is a school on spectral methods in physics, mathematics, and sciences. So by the end of this treatment of large deviation for Markov processes, we will find an eigenvalue problem to be solved, an important one. So, but it's a long way to that problem, and so, but be aware that we will get to spectra at some point. So so before we had our symbols in an alphabet. Now I will change just the way I call things. I will call these the states in some state space. And the idea now is that the state space is finite, so we can depict it by nodes or vertices, or depending on your favorite nomenclature. And then what we allow for is a process that jumps from one node or vertex to another. So we are going to connect these states according to whether or not a transition between two states is possible. Okay, and so what we obtain is a graph representation of the state space where the nodes are the states and the transitions are possible jumps between states. And now the idea of the Markov discrete time Markov chain is that we start from one state and then we hop to a new state with some probability rho omega prime omega. Notice that I use the physicist convention that we put the starting state on the right and the arrival state on the left. Mathematicians do the opposite. Actually, they have good reasons for doing the opposite, but I'm used to physicist convention, so I will stick to this. So this is probability of jumping from omega to omega prime from omega, okay? And we are going to assume two things. One is basically that the graph is connected, that the states communicate, so that it's possible to go from any state to any other state via a path that has non-vanishing probability. So this is communicate. Communicativity, or graph connected. And also, for the sake of physical modeling, it is important to assume that if a transition is possible, then also the reverse transition should be possible. Okay? This is called micro-reversibility. Okay? So we are going to assume micro-reversibility. Also, to make things a little bit easier, okay, now the probabilities of jumping to any other state from state omega, of course, they are normalized. One, of course. And I'm going to assume, to make things slightly more easy, but it's not absolutely necessary, that it's not possible to jump from one state to itself. So I will set all of these to 0. It's just for the sake of this course, but as an exercise I would suggest that people generalize this to arbitrary Markov chains. So I call them Markov chains without self loops. Okay? So now the process can be described, the dynamics of the process can be described in two ways. One is dynamics described by one is single realizations of the process. Single or we can call them trajectories or path or chain or whatever. So that would be up to some time, we call now n plays the role of time in this case. It's just a succession of states. We start from omega 0, we jump to omega 1, and so on until we get to omega n. Okay? And associated to this individual realization of the process is a probability just the product of the probabilities. So it's omega n minus 1 times blah 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 times rho omega 1 omega 0, and then there's an initial probability, which call it P0 of being at omega 0. So we sample omega 0 with this probability P0, and then we jump to 1, to 2, to 3, and so on. Okay, this is one way to describe the process, and sometimes it's called, in large deviation theory, this is called level 3 large deviations, because these are the fundamental probabilities, objects, the path of which we know the probability. And the whole idea is that an observable would be defined along a trajectory. So for example, you can define the number of times that you jumped out of one particular state, or the number of times that you went out of a boundary, or the net number of times that you perform one particular transition, and so on. And that would be an observable defined along the trajectory. In principle, if you want to calculate the probability of this observable, we should take marginals of this probability. But this is a difficult task in general, so we will have to develop some tools. Okay? A different way to describe, we go here. Instead of describing the process trajectory by trajectory, we can otherwise look at the diffusion equation, let's say. The equation, which means, well, that's a physicist way of calling it, but it's just, we define the probability P omega n to be the probability that omega n is some particular state omega, and then this evolves according to sum prime rho omega prime Okay, so we describe the process by the probability of being at some particular state at a given time as an evolution equation. Okay, so notice that this is a linear equation, so we can introduce the vector P n as just P omega n for omega in omega, and then we can write this equation as where R is the transition matrix containing as elements the rows. Okay, so R will be, well, in our particular case, because we decided that we don't have self jumps, then we have rho omega 1, omega 2, rho omega 2, omega 1, and so on. Okay? And of course, the columns of this matrix add up to unity, granting normalization. So if you sum over omega here, you get U1, and then you get sum over omega prime of P omega prime, which is 1. So normalization is preserved. We will call R the transition matrix. Now, under the conditions that I gave before, that the state space is that states communicate and that we have micro-reversibility, then it can be proven that the Markov process has a unique invariant probability or stationary probability. Or stationary probability, which is just the unique eigenvector of R relative to eigenvalue 1, so we call it R rho such that or explicitly we can write this as and it can be shown that any initial state evolves towards rho, that is the limit n to infinity of Pn, which is equal to limit at n to infinity of R to the n times the initial state to 0. This is precisely rho. Okay, so any initial distribution evolves towards the invariant or stationary measure. Okay. Now, physicists would say that okay, look at this law. What this says is that the probability. Oh, sorry, this is rho. Let me write it another way also, because we also know that sum over omega prime, rho omega prime, this is equal to 1, okay? So if I multiply by rho omega, I obtain rho omega, which is this thing here. So I can rewrite this as okay, I just rewrote the steady state equation in a different way, but now this thing here is called the current. Along omega prime. So the current, a current is an anti-symmetric object. Is equal to the net flow of probability from one state to the other. And what this law says is that the sum, so we go at one particular omega, okay, it is connected to other states, omega prime and so on, is that the sum over all omega prime of this current flowing out of omega is 0. So if we represent the current by an outgoing arrow, for example, is the sum of the outgoing currents is 0. This is the Kirchhoff, well, for physicists it's Kirchhoff current law that says that well, basically, charge is conserved at the nodes of the network, okay? But now, of all steady states, well, a steady state always satisfies the Kirchhoff current law with non-vanishing currents, okay? If the currents vanish, then we say that the process satisfies detail balance, okay? So detail balance Markov chains that satisfy detailed balance are a subclass of the set of Markov chains, and they are such that the steady state currents vanish. Equal to 0. Okay. This will not generally be the case. So another way, what physicists also say, when a system satisfies detailed balance, then this stationary probability will be called an equilibrium. So a detailed balance stationary probability is sometimes called an equilibrium. Okay? And notice that we can manipulate this expression as follows. So, omega prime 1 over rho omega equal rho omega prime omega. And this we can write in matrix form. So let me introduce the matrix, let's call it D is equal to the diagonal of rho omega. So I put the stationary state probability in the diagonal in a matrix, okay? And now this writes D minus 1 R D equal R transpose. So this is another way to write detailed balance. And detailed balance is also called time reversibility, which is not micro reversibility that we saw before. Micro reversibility was there exists the opposite rate to every forward rate, but in this case it's really reversibility in time. You can show that the probability of the Markov chain forward with respect to this evolution is equal to the probability of the backward Markov chain with respect to the to the transformation that we propose here. Okay, so next is how do we check that a system satisfies or not detailed balance? From this expression here, from this blackboard here, it seems that you need to know the steady state, right? To know the steady state, you have to solve the steady probability equation, okay? This is not easy to solve. I mean, if the system is large, it's a linear algebra problem, but if the system is large enough, it's a difficult problem. It involves a beautiful math with involving spanning trees and all things that we will not look into. But there is a much simpler criterion for detailed balance, which does not require to calculate the steady state probability. So here, which is called the Kolmogorov criterion. Chemists would call it Beck-Schreiber criterion, and I guess there may be many other names. So the idea is we consider all possible C ranges over all possible cycles in the graph. Okay. So, and what we construct is this object here. Let me call it calligraphic C. Not really calligraphic, but cycle. We take the logarithm of the product of the transitions which belong to the cycle of the ratio, of the ratio of the probabilities forward and backward. Okay? We just construct these objects for each cycle. This is easier than solving the linear algebra problem, also because you don't actually need to perform this calculation over all possible cycles in the graph. You just need a subset of cycles, because then these quantities are additive among cycles, so meaning that the f of two cycles which are combined will just be so basically, because it's a linear function, you just need to work on a basis of cycles. We will see later how to construct one such basis. And so now the Kolmogorov criterion says that if all of these f vanish, then if and only if actually little balance holds. Okay? Okay, so the claim is that Kolmogorov criterion if detailed balance so let's first prove this direction, which is the simpler one. So detailed balance, we can rewrite it as rho omega prime and omega equals rho omega prime, where I remind you that rho is the invariant probability distribution. So now we have to compute these quantities here. So we take a cycle, and f of the cycle, which is sometimes called by physicists thermodynamic forces, or sometimes also affinities. Okay. So for any cycle, we have to show that the thermodynamic forces or affinities vanish. Okay? But this is just the logarithm of the product. So we have our cycle, we take the oriented edges between states, omega prime. We take the logarithm of the product of the probabilities backward to forward along the oriented cycle. So omega prime in cycle of the ratio, but the ratio is rho omega over rho omega prime. But now you see what happens, because you will have rho omega once as the starting state and one as the ending state. So each one particular state will appear once up and once down, once up, once down. Okay, so it will be something like, for example, if this is 1, 2, 3, this is going to be rho 1 over rho 2, rho 2 over rho 3, and then rho 3 over rho 1. All cancel, and this is 0. Okay, so the forward implication is very simple. Now let's look at the backward implication. So we have assumed that f of c is equal to 0, and I want to show that detailed balance holds. Okay, so let me define the following thing: psi omega over psi omega prime. So I fix one omega, let's say omega bar, and I choose one value of psi omega bar. Okay. And now, starting from this particular omega bar, I can reconstruct all other omega by this rule. Sorry, omega bar here. I take, so I have my graph, let's say something like this. So let's say omega bar is the reference state, and I want to find the value psi of omega here. So I consider one particular path that goes from omega bar to omega. For example, okay? This is one path from omega bar to omega, and then I can define psi omega with respect to psi omega bar as just the ratio of the product of the rates along this particular path, okay? So let's call this path gamma, maybe. So I take the product of the transitions omega prime, omega second in gamma of the ratio of the rates. Okay? And now the claim is that this is well defined, that psi omega is well defined in the sense that it does not depend on the path. Okay? Well, if it does depend on the path, let's suppose we take this other path. Okay? Then we can invert the blue path. Okay? So let's invert it. And we created a cycle, right? A red cycle. And if the value of psi omega bar was dependent on the path, then the product of the logarithm of the rates of the probabilities along this cycle would not be zero. Okay? And then we would have a violation of the Kolmogorov condition. Then this is well posed. Okay? It's a good definition of psi. But now let's take psi omega bar, a nearest neighbor of omega bar. So we can write that psi omega is equal to rho omega bar. So this is when, let's say, omega prime is first neighbor. Let's say this is omega prime to omega bar. So omega bar, and we'll take rho omega prime inside omega prime, which tells you that psi must be the invariant probability, the stationary probability, up to normalization. And the normalization you obtain just by fixing the value of this particular starting state. So this is all for